Professor Feryal Ozel. I've known her for many years. She did her undergraduate studies at Columbia University, where she double majored in physics and mathematics. And then she went to Harvard University to pursue a PhD in physics, which she did at the Harvard-Smithsonian Center for Astrophysics, so we used that in grad school. Feryal then won a prestigious Hubble Fellowship, which she took to the Institute for Advanced Study in Princeton for 2 years, and then the third year to the University of Arizona Stewart Observatory, where she's been a faculty ever since. And her one of the world's experts on neutron stars and black holes and how to make measurements of the properties and infer things about the equation of state, which is what she's going to tell us about today. A note for the grad students: I think we scheduled interactions for 2 p.m. at Mannerly, the conference room. So she has to meet with that or not. So, welcome, Feryal.
Howdy.
Howdy.
It's a real pleasure to be here, and thank you for the invitation. I would like to tell you about everything we've done about neutron stars and black holes as far as their masses are concerned, and for neutron stars as far as their radii are concerned in the last 5 years or so. What I would like to start with is their masses, and hopefully this will give us a little bit of insight into their formation. And then the neutron star radii is what's going to provide us with a better handle on their structure, as I will argue in a little while. So this is where things stood about a decade ago. Neutron stars with well-measured masses primarily consisted of double neutron star systems, so where both stars in a binary are neutron stars, and at least one of them is a pulsar, as you can see by this P denotation here. And C is the companion, so this is where the neutron star masses were. And black holes, there were quite a few candidates with large uncertainties in their masses, but about a handful. And the idea was that there is some dividing line between neutron stars and black holes, above which we call them black holes if we can measure their masses well. So why do we want to do this? Let me first motivate it a little bit, and then I'll tell you about the improvements in the past decade. So first of all, this is our way of finding and verifying the existence of black holes. We have to measure their masses, and we have to verify that this is above what a neutron star can support, and that's how we can call them a different population. We want to understand stellar evolution and supernova explosions. What are the outcomes of these? What are the energetics of these? What are the pre-supernova stars like, so that they would produce either a neutron star outcome or a black hole outcome. We want to find the maximum mass of neutron stars and get a handle on the equation of state that way. If we find that there are no neutron stars beyond, for example, 2 solar masses, that's the maximum that can be supported. That will tell us about the equation of state of the interior. We want to perform general relativity tests with these compact objects, which the first step to which is knowing their masses. And we want to understand the gravitational wave signals. What is going to produce the gravitational waves? What are their, do we have the right templates for these merger events? And what do we expect to see with LIGO? Well, how do we measure black hole masses? Well, we rely on black holes in binaries. So if this is your black hole here, this is the companion star. There are attempts to measure masses of black holes, isolated black holes, using microlensing, but I'm not going to get into that. None of the data that I show relies on that. So if it's accreting mass from a companion, the first thing you can look at is the orbital parameters. What is the orbital period? What is the semi-amplitude? But in order to be able to do that for a black hole binary, you wait for a quiescent period. And what I mean by that is all neutrons or all black holes in binaries, when they're accreting from a companion, go through phases where the mass accretion rates are very high. And if you're looking at them with an X-ray telescope, this is the XT, Rossi X-ray Timing Explorer, you see these periods where the fluxes are high and the inferred mass accretion rates are high. But at this point, the luminosity from the accretion disk is dwarfing the luminosity from the companion, so it's not a good time to go and look at the orbital parameters of the companion. You wait for these so-called quiescent periods, here, where you can see the companion directly. When you can do that, what you measure is the radial velocity, and here are some cycles of the companion given for this particular companion of this particular black hole. You will notice that the velocity is in kilometers per second because the velocities are quite a bit higher in a black hole binary compared to, for example, a planet around the star. But also these tend to be more, they are irradiated companions, they are evolved companions, so they tend to be more noisy, which is indicated by the size of these uncertainties, these error bars here. But given that the velocities are so large, it's pretty trivial to measure the semi-amplitude k to high accuracy, determine the orbital period of the system, and that immediately gives you your mass function. Okay? Why is that important? Well, that's the minimum mass that the black hole can have. So at the very least, you have a lower bound on its mass. Now, if you want to go beyond that and ask, what is the mass of the black hole and what is the mass of the companion separately, then you have to know a little bit more about the system. You have to know its inclination, and you have to know the mass ratio. And how do we get at those? So for different systems, of which I'm going to show you about 20 or so here, from Jerry Orosh and collaborators, there are varying levels of data on the inclination of the binary and on the mass ratio. The best constraints come from eclipsing systems where the binary is at a high inclination, so you see eclipses in the light curve. Or alternatively, there are constraints on both the inclination and mass ratio that come from ellipsoidal variations in the light curve. And what that means is that, look at a typical companion. It's pinched towards its black hole companion here. So this is the companion star. It's pinched towards the black hole. When you look at it side view versus when you look at it with the pinch side towards you or the pinch side away from you, there are differences in the brightness of the companion that you see. These are called ellipsoidal variations. So by modeling the ellipsoidal variations in the light curve, you can get a good handle on the properties of the companion and convert that into data on inclinations and mass ratio. Yes?
Why do you call it an ellipsoidal variation if the star is not actually shaped like an ellipse? That's just a convention.
That's just
Okay.
a convention. Okay, so for some systems, we have very good constraints on the inclination of the system and very good constraints on the mass ratio. When you fold that in with the mass function, you get uncertainties that are that look Gaussian. So the likelihood of the over the mass of the black hole looks like a Gaussian. So that's our group 1, where we can model the probability that over the mass of the black hole, given the data that we have, as a central value for the mass and its the central value for the mass and some uncertainty. So this is our highest level group in the sense that both the inclinations and the mass ratios are well modeled. I will show you what these distributions look like so you can see it better. In our second group, there is some constraint on the mass ratio, which is this little q here, but the inclinations are constrained pretty poorly. So we model those with this functional form. And in our third group, actually, there is only one source. It's the microquasar GRS 1915. Because it has jets, its inclination is very well known, but we know very little about the mass ratio. So we can put in the constraints on the inclination right here, but we don't know too much about the Q there. So let me plot these for you to see what the distributions look like. So these are the likelihoods for each and every source on which there is the data that I described. And on the top panel, you see our group 1 plus our group 3, that GRS 1950. And as promised, the uncertainties or the likelihoods do look Gaussian. So you can see a few at around 7 solar masses and a few at higher masses with somewhat larger uncertainties. In the second group, which is shown in the lower panel here, what you will see is that there is a very sharp cutoff at lower masses because of the mass function. Like I said, that's the minimum mass. But because the other parameters are not measured as well, there's an unconstrained probability towards the high masses. So these black holes, this is the most likely mass that this system will have, but it could also be with declining probability at these higher masses. Okay? So now the question is, what is the underlying distribution of stellar mass black holes from which these data could have been drawn, given each and every one of their statistical uncertainties? So to do that, we use the Bayesian analysis technique, and we modeled the underlying distribution as an exponential with a low mass cutoff and asked, what are the most likely parameters of the distribution of the exponential cutoff and the exponential scale that would be consistent with the data that we have? Okay? Now, why did we use an exponential with a low mass cutoff? It's because all the theoretical models lead you to the expectation that if this is the neutron star population that you produce from supernovae following stellar evolution, then the black hole population should look like one that is decaying exponentially. The cutoff comes from the fact that below a certain mass, there will be neutron stars, and above a certain mass, there will be black holes. In this particular plot that I'm showing you, there are many different stellar evolution models and many different supernovae that are being considered, in the sense that there are binaries and singles, and there are different prescriptions for winds. But if you account for, even with its uncertainties, what we know about supernova explosions, stellar evolution, and the stellar mass function, which always declines towards high masses, then the expectation is that there should be a continuous distribution with the most number of black holes at the lower masses and exponentially decaying towards higher masses. So this is the model that we are going to work with, and we took priors over this decay scale in the exponential and the cutoff mass that are flat. For the cutoff mass, it's flat between 2 and 8 solar masses, although there's almost no sensitivity to the priors that we take for this analysis. And the cutoff scale, we got anything from 0.1 solar masses to about 20 solar masses, a flat prior. So because there is no real reason to prefer one over the other. So given the individual data, we wanted to infer the most likely values of these two parameters of the underlying distribution. What we got was very, very surprising. What our data tell us is that the most likely value for the cutoff mass is just over 6 solar masses, and the most likely value for this scale in the exponential with which the black hole mass distribution decays is about 1.2 solar masses. Okay? So compare that to the theoretical expectations, where I took all of those curves and converted them into what their distributions in cutoff mass and scale would be like. the cutoff mass should be somewhere between 2 and about 2.5 solar masses, and the scale should be somewhere between about 3 and 9 solar masses, based on all of those calculations that I showed you. Now, if you look at the 95% confidence level, you still conclude that there are, in the underlying distribution, there are no black holes below 5 solar masses, and the scale in the exponential can be as small as about 0.2 solar masses and maybe as large as about 5.5 solar masses. So a very narrow distribution. I'm going to show you this distribution, but let me first go through the neutron star masses so I can combine the two. You might also wonder, is this a selection effect? That is the observational protocol somehow selecting black holes at 10 solar masses, or 8 solar masses rather, as opposed to 3 or 4 solar masses? And we've looked into every aspect of the observational procedure, and we cannot identify a selection effect that would give rise to this result. How about neutron stars? What do we know? Well, we again rely on sources in binaries. I don't know if you can see this at all. This is just meant to be a pulsar and its companion. Most of the neutron star mass measurements are done for pulsars, where pulsar timing gives us microsecond resolution data. Again, the binary mass function is measured. And in addition, 1 or 2 of the 5 post-Keplerian parameters are measured. What are these post-Keplerian parameters? It could be, for example, a Shapiro delay when the neutron star the binary is at a high inclination and the pulse from the neutron star goes through the gravitational field of its companion. So the range and shape of that. It could be an orbital period decay. It could be the time dilation. So if 2 of these post-Keplerian parameters are measured, we're again in the case where the system is very well constrained and the errors are Gaussian. If 1 is measured, then it's equivalent to our second category in black holes, where we have good constraints but unconstrained, but still a tail that we can't quite pin down. Now, either this with the binary mass function, or in some cases of observations of a white dwarf companion and spectral modeling of the companion, that gives the white dwarf mass. Or a third category where I will show you some mass measurements with thermonuclear bursts on neutron stars. So for neutron stars, we not only divide it by data quality, how many post-Keplerian parameters, how many constraints, but we also divide by source type. The reason for that is that there are some neutron stars that are thought to be near their birth masses because they have a young companion, or they're in a double neutron star system where there couldn't have been significant mass transfer between the two. Or some that have gone through a fairly significant accretion period, and they could have gained quite a bit of weight during that time. So the source types that we can identify are double neutron star systems, which are shown in these gray, in green points here. We have 6 pairs of double neutron stars with well-constrained masses, plus 3 with only 1 post-Keplerian parameter, plus 9 neutron star white dwarf systems with precisely measured masses, so the highest quality data. There are 31 more neutron stars with reasonably well-determined masses. I'm not going to go through all the subcategories of whether they are near their birth masses or they have evolved away from it, given the data quality, but I want to show you 2 examples of these subcategories so you know what I'm talking about. I'm again plotting the likelihood over the mass for individual objects. There are 6 double neutron star systems here. You will see that the uncertainties are again Gaussian. but the Gaussians are actually so narrow that they look almost like delta functions because the timing is done so precisely over such a long baseline for these systems. So these are those 12 neutron stars. And as a second example, let me show you what I call fast pulsars, those that have gone through an accretion period, and the likelihoods over their masses. What you will notice is that the cutoff now is at high masses. It's the mirror symmetric of what we had for black holes. Why is that? It's because for black holes we time the companion, but for neutron stars we time the neutron star itself. So the binary mass function here gives you an upper limit on the neutron star mass with some tail extending to lower masses. These two red curves have white dwarf companions. That's why they're colored in red. Okay, so let's ask the same question. Given the observations, given these data, what are the most likely distributions that for the entire population from which these sources could have come from, given the uncertainties that we have in the measurements? Dividing it into three categories, what I call recycled are the ones that have had an accretion phase, double neutron star systems, those 12 plus 6 sources, and high mass X-ray binaries and slow pulsars, which are also thought to be near their birth masses. The first thing to notice is that the double neutron star population is very, very narrow, and it's centered at 1.35 solar masses. 1.35, you might think, is close to the white dwarf Chandrasekhar mass, so maybe it has something to do with that. Well, it doesn't, because that's the baryonic mass. So if a 1.4 solar mass iron core collapses, with the neutrino losses, you would be left with about 1.2 solar masses of a neutron star. 1.35 is very difficult to understand from the nuclear stellar astrophysics point of view. On top of that, it's also extremely narrow compared to, for example, other neutron stars near their birth masses or the recycled neutron stars. Now, let me show you in a different way why the double neutron star distribution is anomalously narrow. So here, now I'm plotting just the Gaussian dispersion and the central mass of the distribution. The double neutron star most likely value is right here, and this is the 68 and 95% confidence contours. What you get from supernovae, assuming no fallback, is either electron capture supernovae, which can produce a very narrow distribution here, or other mass losses that can produce anything from about roughly 1.1 to 1.2 solar masses, core mass. Now you might say, well, perhaps the supernova explosion doesn't eject the entire envelope, so some of it falls back onto the system. And this is commonly seen in supernova theoretical calculations, that there is some amount of fallback. Well, whatever adds mass and gets you to higher central masses also increases the dispersion along this line. So core collapse supernovae, whether you do it from very basic theoretical considerations or from extensive numerical simulations from the Santa Cruz group, for example, what it says is that surely you can move neutron stars to higher masses, but not without increasing the dispersion of that distribution. So when you look at other slow pulsars, for example, their distribution is perfectly consistent with core collapse supernovae with some fallback, whereas the double neutron star systems are here excluded at several sigma from those systems. So this is a mystery. I'm not going to have a solution to this. I'm not going to offer a solution to this in this talk. But let me go back to this point that the black holes are also not where we expect. And to make this a little bit more visually clear now, what I've done is taken the most likely distribution of the recycled neutron stars the ones that have gained as much mass as they could during their lifetime. And now I'm comparing it with distribution over the black hole masses. This is the most likely, and this is integrated over the entire distribution. Same thing here, most likely and integrated over the entire distribution in solid. This is the mass gap that I'm talking about. First of all, there is no indication from these data that the maximum mass of a neutron star has played a role in shaping the recycled neutron star distribution. We don't have a rising distribution that sharply cuts off. Instead, there are a few sources out here, but it's at the tail end of the distribution. And again, when we compare these two, where we expect the most number of black holes, there's a desert. Okay? What could give rise to this? For this, we have a little more of an idea. This could be a group of, or a range of masses in the progenitors that actually lead to failed supernovae. So we suggested this in our papers, and Chris Kochanek developed it further just a couple months ago. There was a paper out on AstroPH, and Woosley and Hager and Woosley and Lovegrove also ran supernovae calculations and stellar evolution calculations that support this idea that there could be a range of masses that produce failed supernovae. So the idea goes something like this. Don't take these numbers at face value. There's a lot of wiggle room, but roughly at below 15 solar masses pre-supernova mass, there are successful supernovae, ejects all the envelope, no fallback, leaves a neutron star remnant.
Excuse me, progenitor here is the initial mass of the star, or the mass of the star that was falling down?
This is the initial mass. So pre-supernova mass could be smaller than these because of mass losses during the evolution.
It would be significant mass.
Exactly, especially out on this end. So between 16 to 25 solar masses, give or take, the structure of the neutron star is very conducive to just imploding, with the only exception that the hydrogen envelope is very loosely bound, so that might be ejected during this process. So you have a direct collapse where the remnant is the entire helium core mass, and that is roughly around 8 solar masses. Of course, there's a dependence on the stellar mass, but that could give rise to that narrow distribution we are seeing in the black holes. And above about 25 solar masses, there's quite significant mass loss prior to becoming a supernova. So a lot more of the envelope is ejected, and these stars could explode successfully. So these and these could be successful type 2 supernovae, and this could be the missing progenitor mass that fail, and they produce black holes via direct collapse. And that's why we get this pretty narrow black hole mass distribution. This is plausible. I think it needs to be explored more. So in the next year or two, I think we'll make more progress on this.
Nice, silly question. So do the greater than 25 solar mass progenitors lead to black holes, neutron stars? Neither.
Both. So it's non-monotonic. So you produce neutron stars, then you produce black holes, then there's a sweet spot again where you can produce neutron stars, not at all in a way that explains how narrow the double neutron star mass distribution is, but at least it produces neutron star masses, and then it produces black holes again. Other questions?
Why can't you form a black hole just from accreting mass onto it?
That's a very good question. Where are the systems from accretion-induced collapse? So even if you didn't produce it at the supernova stage, if you feed a neutron star for 1 billion years and just feed it a little too much, you should be able to push them over the edge and still fill that gap via that process. So the only explanation I have for that, and I don't know if it's the right one, is that somehow the recycling process, this mass accretion process onto neutron stars is pretty inefficient. So all in all, it's able to add about 0.2 solar masses. That's the difference between the means of those two distributions. But there are very, very few systems that actually, just by eating, get out here. So this could be due to the magnetic field of the neutron star. It could be due to other processes that affect accretion onto neutron stars. But it seems that when you find a neutron star with a white dwarf companion or a low mass X-ray binary, really they haven't gained all that much mass. What you would expect from, for example, Bondi rates or other sample estimates.
But isn't in the accretion disk model most of the mass blown away from heating up and pulsar activity, and not too much of it gets onto a black hole when you have an accretion?
So you're talking about the accretion phase onto a normal neutron star from a companion that's evolving. Yes, so, well, if you do a very simple estimate, like what is the Bondi capture rate, then you expect all of them to evolve out here. But the magnetic field plays a role. There's a propeller mechanism, and there are other suppressions that we can think of the mass accretion rate onto neutron stars that make that process less efficient than you would think from simple considerations. And I think that's what you're saying, right? That it's not, I mean, maybe we should never have expected it to be that efficient.
Just last week, we heard about a colloquium in which the accretion onto the neutron star causes nuclear reaction, which is called gamma bursts. So all the mass basically irradiated away, so you don't accumulate.
That's possible. I'll also show you examples of thermonuclear bursts that are observed in the X-rays. And in those systems, yes, there is mass loss, but I think the cumulative accumulated material is not all that much. Yeah, both because of mass loss during explosions and because of barriers to accretion in the first place. Okay, so let me move on to the second half, which is neutron star radii. How do we get a handle on neutron star radii? What are they good for, and what do we know so far? Well, the I'm sorry, the PowerPoint thinks ultra dense is a misspelled here, so that's why it's underlined. The ultimate goal is the physics of cold ultra-dense matter. So what we are really trying to understand is neutron star cores can reach about 10 times the nuclear saturation density. What happens to matter at those very large densities when the temperature is low? So this is a different regime of the QCD phase diagram than, for example, the quark-gluon plasma or early universe. And we typically show a cartoon to explain what we might expect. And we say, well, if they remain as neutrons, if they remain as nuclear matter all the way down to the core at these very high densities, then the neutron star will have a different structure than, for example, if they become strange quark matter or there are phase transitions like condensates of kaons or pions or restoration of chiral symmetry. So this type of a star would look different than a star where nucleons remain as nucleons all the way up to many times the nuclear saturation density. How do we get at this? Well, again, we look at the neutron star black hole division, see if there is any evidence for that from the highest mass neutron stars. We want to understand the supernova mechanism that also affects is affected by the neutron star radii, because the neutrinos that are produced by a system like this versus a system like this are different. We want to understand GRB durations. For the long duration GRBs, the prevailing model is that of a collapsar, that you first form a neutron star that is rotating rapidly, and as it slows down, it collapses into a black hole. Does that really materialize? And again, we want to understand the nature of gravitational waves. The final stages of coalescence is sensitive to the neutron star interior. So, how are we going to measure the properties of the interiors? How are we going to get at the physics of cold ultradense matter? What I'm going to show you is that measuring the radii are the best way to do this. Again, just from a cartoon point of view, this is a bigger star than that one, so maybe if we find bigger radii rather than small radii, this will tell us something about the interior. Luckily, we've gone well beyond just staring at cartoons, and we actually established a mechanism for converting neutron star radius measurements directly into nuclear physics quantities. To illustrate that, what I'm going to show you here is a range of proposed equations of state. This is pressure, this is density. You see many orders of magnitude here, many orders of magnitude here. The proposed equations of state look something like this. Quite a bit of uncertainty. Out here, we think we know what we're doing from terrestrial experiments. As you go to higher densities, the uncertainty increases. This is roughly twice, 4 times, and 8 times the nuclear saturation density, where all the uncertainty starts kicking in. Now, for each one of these curves, by solving the Tolman-Oppenheimer-Volkoff equations, the neutron star structure equations, you can produce a mass-radius relation, right? So they look something like that. You put the mass on the y-axis, radius here, and you have, for each one of those curves, a mass-radius relation here. There's quite a bit of uncertainty even within certain models. These are, for example, this is a kaon condensate. This is an older nuclear physics model. And this is the nuclear physics model that goes through all the current data, scattering data, levels of light nuclei, etc. So, for each one of these we can produce that, but this is a whole curve, this is a whole curve. There is no hope that we will find neutron stars that line up on this curve so that we could hope to have a complete inversion to the equation of state. Luckily, we don't need it. It turns out that if you parameterize your equation of state in a smart way and just say, I know what's going on out here, if you just tell me the pressure here, here, and here, and I connect them by piecewise polytropes, and I solve my equations and get the mass radius relation for that limited knowledge of the equation of state and compare it with the full knowledge of the equation of state, I do extremely well. So that's the difference between the dashed and the solid curves. Solid curves are the full knowledge of the equation of state. Dashed ones take only those 3 parameters. Tell me the pressure at these 3 fiducial densities, and I'll reconstruct the mass radius relation for you. Those are these dashed lines. This is some work that we've done back in 2009 and published in PRB. So what's the good news here? The good news is that you now have a target for what you need to measure and how well you need to measure it. Because if I tell you I've reduced the entire equation of state into 3 parameters, then you might say, well then, if you measure radii of 3 neutron stars, you might be able to solve the full problem. That's indeed correct, and here is some illustration of it. Let's say that the underlying equation of state is FPS. This is simulated data. And let's say that I have 3 neutron stars whose radii and masses I've measured to within 5% or 10% uncertainty, shown here. If you just give me these, and I don't know the underlying equation of state, and I do the inversion technique that I just told you about with the parameterized equation of state, what I would conclude is that these are just some confidence contours over the that pressure at the third fiducial point and the pressure at the second fiducial point. This is the most likely value, and this is 68 and 95% confidence confidence. So notice what happened. FPS is smack in the middle of it. GS1, my other fiducial equation of state, just as a point of comparison, is excluded, and AP3 is excluded. Okay, so this inversion really works. And you can get a faithful recovery of the equation of state. So,
Can you remind us what is the FPS, what is the word?
oh, it's an older nuclear equation of state. That's, it's just an example here. I'm not advocating FPS in any way.
But I would like to know what the order.
Sorry?
Do you remember the orders for that word, for the equation of state?
The authors. Oh,
That's all, okay, actually.
this is the Akmal and Pandey. This is the Beta and Brown.
Okay.
FPS, who are the authors? I'll look it up after the talk. Okay, so hopefully this convinces you that looking at neutron star radii is really going to pin down the nuclear physics of the interior, and that it's sufficient to do this for 3 sources. Of course, more is better, but a minimum of 3 with about 10% uncertainty. That way we can really pin down what the equation of state looks like. Now, this is a little bit of like easier said than done situation, in the sense that when you go and try to measure neutron star radii, you face 2 complications. The first is that if you were dealing with a normal star, to get its area, the emitting area, you would measure the observed flux. You would multiply it by the distance squared, divided by sigma t to the 4th, where t is the effective temperature of your star, and you would get the emitting area on the star. Okay, and then you would call this your surface area of your star. Because neutron stars are very compact, general relativistic effects come into play. And even if you looked at a slowly rotating neutron star and you said the exterior spacetime is just Schwarzschild, what that does is introduces a correction, 1 minus 2 gm over rc squared to the -1, that turns the left-hand side into an apparent radius, what the neutron star appears to be, but given the mass of the neutron star, its actual radius is going to be different from that. That's the first complication. The second one is that you have to find neutron stars where you see the surface, the whole surface, and nothing but the neutron star surface. Okay? So help you God. The reason I say this is that neutron stars, if they're accreting, can have contribution from the accretion disk. They can have a contribution from the magnetosphere if they're isolated. You might be looking at polar caps rather than the whole neutron star surface. How are you going to persuade yourself that what you're seeing is the whole surface and it's uniformly emitting? Well, there are 2 windows onto neutron star surfaces that we can utilize for this measurement. This is just like what I was showing you earlier for black holes, but for a neutron star system. The tick marks don't show here, but these are time scales of years. And again, this is an X-ray count as a function of time. There are periods of outbursts where mass accretion rate is high, and there are periods of quiescence in between where accretion ceases and the neutron star is just visible by itself. In these systems, these low mass X-ray binaries, there are 2 advantages. One is that the magnetic field strengths are low. They're dynamically unimportant, so that if there's material coming onto the surface, it would spread over the whole surface. And also, you wouldn't see a polar cap emission. You would see emission coming from the whole star. So for these reasons, these are the best targets if you want to measure neutron star radii. In the first one, let me let me try to show you the animation here. In the quiescent phases, what we rely on is the fact that once the accretion, or during the accretion, the neutron star surface is heated up. Actually, there are very nice nuclear reactions going on there. Also, some of this heat is conducted into the core, so it keeps the core hot for a long period of time. Once the accretion ceases, what you see is the re-radiation of that stored heat on the neutron star surface. So you utilize that period and look at the so-called quiescent luminosity in order to measure the neutron star radius. Now, you want to make sure that sorry, these are technical problems with the projectors. The bottom wasn't showing, that's why I'm showing you the whole talk in this mode. Okay, good. You want to make sure that the accretion really ceased during these quiescent periods when you're looking at the surface. So for example, the source that I'm showing you has 5 Chandra observations carried out in different epochs, different quiescent phases separated by years. The spectrum does look thermal, so that's very good. The non-thermal component is almost negligible. And the spectrum also looks very similar at numerous quiescent periods, so that gives you more confidence that what you're seeing is the stellar surface. Using these, you can look at the mass-radius relation of the quiescent neutron star, and what you see are these bands, these contours, that give you a combination of the neutron star mass and radius. Okay? So because of that GR complication, what the best you can do is to pin down the mass and radius into these bands. Now, this one is a heavily piled up observation. We just got a program approved on Chandra to redo it, so I'm not going to show you this again, but what you will see is that these neutron stars are roughly at 9, 10, 11 kilometers. Okay?
What does it mean by that?
So the readout time on the Chandra CCD is 8 seconds, and during that time, about 20% of the pixels had more than 1 photon arriving. So you cannot tell the difference between 2 separate lower energy photons versus 1 high energy photon. So it had to, for this particular source, you could use, for example, only 1/4 of the CCD and reduce the pile up that way. Okay. And of course, I should also mention these measurements rely on modeling the spectrum. So a pile up that takes a softer spectrum and makes it a harder spectrum, really affects what radius you measure. Okay, the second window is during the accretion phase, but there are some events that are caused by accretion that actually dwarf the accretion luminosity for a short period of time. Okay? The underlying physics is that when material is accreted onto the neutron star surface, it gets compressed and it gets to higher temperatures and higher pressure. And at some point, the triple alpha reaction is ignited at the base of this accretion column, and it burns unstably and gives rise to these so-called thermonuclear bursts. So I have a little movie here showing that if it's ignited at one spot on the neutron star surface and there's a deflagration wave, it proceeds very quickly throughout the entire star surface. And great, I can just show that to you one more time. So as long as there is fuel, This process, it takes much less than a second, and the entire stellar surface is engulfed by this thermonuclear flame, and it starts shining brightly in the X-rays. So if you were looking at it with an X-ray telescope, what you would see is a sudden rise in the flux within a second, followed by a decay. And if you divided this up and asked what is the spectrum doing, what's the temperature doing, you would see that the temperature would shoot up to about 2.5 keV or so, and then slowly decay as all the energy generated through the thermonuclear reactions turns into photons and diffuses outward from the star. If you take the flux and divide by T⁴, what you see is that the emitting area has a sharp increase and then stays roughly constant, and then the data get noisy. Okay? So if this is indeed what's happening, that the entire neutron star contributes to this thermonuclear burst, and the emitting area stays constant, what you expect is that if you plotted the flux versus the temperature of the spectrum, the so-called color temperature, you would expect it to follow a T⁴ line. So, or a constant line here. Astronomers like to use what's called an HR diagram. So this is the flux, and the temperature for historical reasons increases to the left here. So what I'm saying is, if this burst really does what I'm saying it does, the data should fall on this line. Will it? Well, watch it pretty much in real time. This is the time running in seconds, and this is what that burst is doing. Okay? Don't worry about this. This is the expansion of the photosphere above the neutron star surface. But the rest of the time, it really has a constant emitting area. Now, how do you know that I'm not showing you the one best case and everything else is just terrible? So let me show you the statistics on this. Okay, I picked sources where there are lots of bursts. So bursts separated by 10 years. Each one of them 10, 15, 20 seconds, but happening over and over and over and over again. So what you see, again, color temperature increasing to the left, flux on the y-axis, is that they follow beautifully a T⁴ line. On this source, there are more than 100 bursts. And something that I want you to pay attention to is that the flux at the peak of the burst and flux at the tail of the burst is different by an order of magnitude. We still have to subtract the background luminosity. Out here where we can do that well, there's a very well-defined T⁴ track. Down here, there is noise introduced by other processes that we can't control at very low flux levels. So again, these are thousands of data points that follow T⁴ line for different sources.
Why would you expect a unique temperature if it's a deflagration process on an axisymmetric system? It would seem like deflagration would be messy. You'd have the flame increasing and decreasing in areas. If it was a detonation, it would seem like they'd have a unique temperature. Deflagration, at least when we do hydrodynamics of explosions and supernovae, it's not constant. You have a range in temperature, which would also probably mimic something like this too.
Correct. So we cannot fully rule out the fact that there is some patchiness on the neutron star surface. But the effect of that patchiness is the uncertainty for, at each temperature, what is the range of the fluxes. So let me answer your question in two ways. One, we're not sure that it's a deflagration process, that it could be a detonation wave also. So that we've run simulations where it's detonation and deflagration. Detonation obviously proceeds very, very quickly. But even when it's deflagration, the surface seems to burn uniformly. The other way to address that is, okay, let's say that there is some composition non-uniformity or temperature non-uniformity because of the flame propagation on the neutron star surface. How much of a role does it play in broadening that? So ultimately we're asking, is this a delta function that the same, exact same surface area is contributing to all these events? Or is there something that's broadening it, some systematic uncertainty, and that would go under that category. Same thing with the cooling. If there is non-uniform cooling on the neutron star surface, not just burning, but non-uniform cooling, that would introduce a systematic uncertainty on the emitting radius. So we used these data to quantify exactly that question. How much of a systematic uncertainty is there in the underlying radius? Now, using thermonuclear bursts has another advantage, which is that in addition to the apparent radius, you can also measure the Eddington limit, where in some bursts, the flux that is produced by the burst is so strong that it actually lifts up the photosphere and it stays there for a little while before contracting back onto the neutron star surface, and then it stays constant. The way you see this is that the temperature rises, falls during the expansion phase, rises again in the contraction phase, and then the whole thing cools off. Okay? This is great because in an event like this, it means that the radiation force and the gravitational force are balanced, which gives you another handle on the mass radius combination. You can ask the same thing. Can I, if I see multiple Eddington limited bursts from the same source, does it come to the same flux? Is this something really intrinsic, like in the type 1a supernovae? Do I actually have that as a standard candle? And in this particular source, there are 5 Eddington limited bursts, and the fluxes are shown in these yellow dashed lines. So this is the level of uncertainty, or the scatter, rather, we see in different Eddington limits measured from different bursts. So indeed, for any source where we have more than 2 Eddington limited phenomenon, they are statistically consistent with being a single number. So this is the apparent radius curve. This is the Eddington limit curve. We're going to look at where they intersect. I'm not going to have any time to get into distance measurements, but for those in globular clusters, we use the distance to the globular cluster, and these are the likelihoods over the mass and radius of this particular source. The probability distribution is double peaked, so two most likely islands form the 68%, and the purple is the 95% confidence contour. We have 5 of these in total, in addition to the 5 from quiescent globular, quiescent low mass X-ray binaries. So here is the compilation from a recent review I wrote for reports on progress in physics. The butterfly shapes here are the 95% confidence contours for each one of these sources. These are what I showed you earlier from globular cluster quiescent sources. And what I want to point out here is that, first of all, these are different techniques. The results need not have agreed, but they do. By now we're up to 10 sources, and they all show consistent radii. And second, they are actually all smaller than an equation of state like AP4, which is the most modern nuclear equation of state. Okay? So we're not saying they are scattered around AP4. You can see that all of the radii are to the left of AP4. So that means that if you just took your vanilla nuclear equation of state and said nothing new happens at high densities, the radii that are predicted by that are too big to be consistent with what is currently being measured. Let me show it to you on the pressure density relation here. The hatched region is what is consistent with the measurements. These are the pressures at those 3 fiducial densities that I described earlier. Of course, at low densities, there is agreement with AP4, but as we go to higher densities, what we're saying is that the equation of state needs to be softer than what is predicted by AP4, which is, as you can see, a straight extrapolation to higher densities. So something needs to be softening the equation of state. One of the likely candidates is quark degrees of freedom appearing in the cores at those high densities. But regardless, there is some indication for new degrees of freedom appearing to make the radii consistent with nuclear physics predictions. So here are my conclusions. The radii tell us already something pretty specific about the interior. We have measurements at least 3 fiducial densities that we can use to constrain nuclear physics. And the mass gap might have its origins in the pre-supernova stars and the details of the supernova explosion, but the narrowness of the double neutron star distribution is right now a puzzle that we don't have good ideas about. Okay, so I'm just going to leave up the slide, which is what the future will bring. The NICER is a NASA Explorer class mission that's already approved. It's going to go on the space station in 2015 or 16 launch date. And LOFT made it to the last round. It's an N-class mission that was down selected by ESA. It's going to go up for its last round of competition in a few months. And they are going to produce data on neutron stars that is orthogonal to what I presented today from the spectra. They're going to look at light curves, and the amplitudes and the shapes of the light curves encode information about the neutron star mass and radius. So this is going to be a great way to move forward in checking any results that I presented today. Thank you.
Thank you, Feryal, for a very interesting talk. We have time for a couple more questions. Anybody wants to ask more?
So from the